This module is really all about kind of introducing you a little bit to the synthesis of some coordination compounds. It is also an introduction a little bit to the use of some of the spectroscopic tools you learned in Module 1 to some problems in chemical kinetics. So what I'll do today is kind of describe a little bit about the coordination chemistry of metal centers. I know some of you have had 503, many of you may have not. I'm trying to equalize the sort of knowledge base by what we do today, and then I'll walk through a few examples of ligand substitution reactions, which are something you'll explore in the class as well. So, you know, sort of foundational people that were involved in the development of chemical kinetics. This person, Arrhenius, received the Nobel Prize in 1903. Werner, who contributed really, I would say, the foundational work in coordination chemistry, at least descriptive coordination chemistry, and the sort of person who really made a true science out of the sort of kinetics of ligand exchange reactions, so much so that our lexicon is really defined a lot by his contributions, is Henry Towne, who was a Nobel Prize winner many, many years later. Okay, so what's the goal here? We're going to introduce some basic aspects of the synthesis of simple coordination compounds. We'll introduce a little bit about IR and visible spectroscopy that you've also seen in Module 1. And in particular, do some work on probing the kinetics of substitution in transition metal centers and how you may understand mechanisms. So these are the d orbitals. All of you have seen these at one point or another in 511-2 or in other classes since then. These orbitals for most transition metals compose the frontier orbital manifolds. The HOMOs and the LUMOs are going to be some assemblage of these orbitals, and as a result, having an appreciation for their spatial distribution, their shape, and ultimately how their population gives rise to reactivity is a big element of the subject of inorganic chemistry. And so if we consider a homoleptic meaning all of the ligands are the same, coordination compound that is of essentially octahedral symmetry with 6 amine molecules around a cobalt center, or bound to a cobalt center. This overall ion is 2+, and so the question we're going to ask ourselves at a very, very basic level is, in this sort of a geometry, how are the energies of these orbitals going to change? Now these are orbitals that are approximated from the hydrogenic wave functions, right? And so in the limit that there is no breaking of the symmetry around the central atom, for say a hydrogen atom, these orbitals would all be the same energy. But as the ligands impose a field, an asymmetric environment of electron donation around the metal center, they will alter the characteristic. Excuse me. Alter the characteristic energies of these orbitals. And so that's kind of the question that we're going to ask. How will the ligands impact the energy of these orbitals? So by a show of hands, how many have that? 5 and 3? Okay, so some fraction. But again, I want to level the kind of understanding that everyone has. So again, if you begin with these d orbitals, right, they'll all be degenerate or the same energy before I impose any ligand field on them. And then when I bring in the ligands, does anyone want to volunteer a guess as to which orbitals will be most affected by this? These ligands? In a situation that, again, the ligands are oriented along the z, x, and y axes?
dz squared and dx squared minus y squared?
Yes. So the ligands that are influenced the most are those that are actually interacting directly with the ligand orbitals, right? So the ligand comes in with essentially an sp hybrid orbital that is interacting with the d orbitals of the metal center, and of course there are going to be some orbitals here that have local density that's pointed directly at the ligands. And in those cases, the interaction of the ligand with those orbitals will cause the orbitals that are mainly d orbital parentage to be raised up in energy. What we'll see in a moment is that this is because these are anti-bonding orbitals with respect to the ligand. But the fundamental appreciation is that you get a ligand field splitting, or in other words, the field, the asymmetric electron donating environment of these ligands induces a field on these orbitals that splits two of them to be at a different energy than the other three. And these other three are the ones that are not pointed at the ligands, the DXY, DXE, and the DYZ orbitals. Does this make sense? Probably, again, something you've seen in 511.2 a little bit. 511.2 a little bit. So, okay. So what really, okay, let's ask a simple question. For the cobalt center here, how many d electrons does that possess? Five. So how do we determine that? So what group is cobalt in? 7, okay. So the way to look at it is to identify what group of the periodic table the cobalt is in, and because it's 2+, that means that 2 electrons have been removed from that d manifold, and it turns out that the number of electrons that remain are 7 electrons here. And so if there are 7 electrons here, there are of course several ways in which we can populate these electrons. We can populate them with all of the electrons spin paired, or with the electrons spin to minimize the amount of spin pairing, or we can do something intermediate. Right? So if I, for example, fill them with 1 electron here, 1 electron here, 1 electron here, then 1 here and 1 here, that would be 5 total, and then I'd have to spin pair the remaining 2, right? And then that would lead to what's known as a high spin complex. I could also have a low spin configuration where I have 1, 2, 3, 4, 5, 6, and the last one here. And that would lead to different spin states for this metal center, something we'll ultimately see will in fact impact its reactivity. One other parameter that you'll appreciate from this, and this will certainly be dependent on the nature of the donating power of these ligands, is that there will be a ligand field splitting. Right? The stronger or the more basic, if you will, these ligands are, they will have a stronger influence in an anti-bonding sense in terms of pushing these orbitals up in energy. And so what we're going to look at over the next few slides a little bit is what are the contributions that give rise to different field splittings. And then ultimately we'll ask how that relates to reactivity. So the first thing you can consider is that if you had a ligand that was only interacting in a sigma fashion, that is, it only had a lobe that was pointing directly along the internuclear axis of the metal ligand bond. And that's certainly the case for the hexaamine cobalt compound that I showed in the previous case. And as a result, you would get splitting that's simply related to how strong of a donor that amine molecule was. And it would, of course, raise 2 of those orbitals, which would have a character that is metal ligand sigma antibonding. The reason is that the amine orbital is lower in energy, and so there's a bonding pair below, but the d orbital manifold has an antibonding interaction with that orbital, and so you have metal ligand antibonding orbitals that are higher in energy than the non-bonding orbitals that are not pointed at the ligands. Now I have the possibility of not only having the donation along the internuclear axis, but also orthogonal to the internuclear axis. What I guess I mean by that is, say I have a metal here with an amine, right? In this case, I have a lobe like this that's interacting with lobes on the metal center in this sort of a fashion. But what if I instead have some ligand where now I have the opportunity to have not only lobes interacting like this, but also lobes that were orthogonal, right? Now there would be other orbitals on the metal center that would have the ability to interact with these orbitals in addition to the interaction along the internuclear axis. Can anyone think of a ligand where that would be an effect? Cyanide would be one example. Now cyanide would not be a donor. A donor would be something like a halide, like a chloride or an iodide or a bromide. Donor meaning that these orbitals that are interacting with this metal center in this fashion are filled. And as a result of them being filled, they will take on bonding and anti-bonding character with these other orbitals that used to previously be these non-bonding orbitals. Right? So remember, the non-bonding orbitals in the sigma-only case are the ones that are not pointed at the ligands, but because the ligands themselves have other orbitals, they can interact with these non-bonding orbitals, make them formally pi antibonding, and that can occur to create pi when you have a pi donor. As you mentioned, for something like a cyanide, you can also have a pi acceptor, and that's because the cyanide molecule itself has low-lying antibonding orbitals that are unoccupied that are essentially high up here, and they can interact in a constructive fashion or a bonding sense with these previously pi non-bonding orbitals. Right? And that would lower this energy, and you can see here that by virtue of what ligand you pick on the metal center, you'll create a different degree of splitting between the d pi orbitals and the d sigma orbitals, or in other words, between the dx squared minus y squared and dz squared versus the dx e y z and x y. Does this picture make some sense? Okay, good. Please feel free to. Okay, go ahead.
Sigma only, you just change the DG center.
In the sigma only case, yeah. So what is? Wait, just repeat the question.
Oh, do you just do that with the top two?
You mean between these cases, or?
Like compared to like without any ligands.
Ah, yes. Compared to without any ligands, right? These become antibonding, and so in other words, all 5 orbitals would be at this level, and it's these 2 that are raised up. Sasha?
Yeah, I was gonna.
Okay, so why does this matter, right? So the ligand field splitting determines an awful lot about the behavior of metal centers. It not only determines some basic things like what their color is, right? So the nature of the ligand you have on a metal actually will change its color. And in fact, this is what we'll talk about in the next moment, known as the spectrochemical series. Is really a reflection of that different ligands will impose different splittings of the d orbital manifold, and that will then cause a change in the color or the energy of the light that's absorbed when you shine a broad spectrum light on these centers. It will also impact the spin population of these centers, and that will impact their magnetic properties. It will impact their reactivity, which will be the main concern of what we'll do here, although the color will also matter because we'll monitor their color spectroscopically in order to determine something about their reactivity. And ultimately, much of life is really only possible because of all of life is only possible because of the reactivity of these metal centers, and so their ligand field chemistry, of course, matters a lot for determining how we function biologically. Okay, so what we can now do is essentially characterize what's known as the spectrochemical series, which is simply looking at how field strength varies as a function of different changes in the ligand, right? So the way we're going to do this is we're going to take the exact same metal center and the exact same oxidation state and compare the splitting, and a higher number means that it's, of course, farther split, right, between different ligands. And what you can see here is that for vanadium ions in the 3+ oxidation state, and all water ligand field will give rise to a certain degree of splitting. If I have something like a fluoride or a chloride that is a much better pi donor, that actually reduces that gap, and you can see a change from 18,000 to 16,000 to 12,000, indicating that pi donation is causing a shrinking of the orbital energy separation between the d pi and the d sigma orbitals. Whereas if you give it something like a cyanide, you go in the opposite direction. You actually increase the orbital splitting, and the same sort of exact effect can be observed for rhodium, where you have, say, a rhodium water, amine, and a chloride. And you can see the different effects here. Water is a weaker donor than the amine, so amine causes it to go up in energy. Or in other words, an amine is more basic than that of water. For a chloride, you will lower that splitting, and for something like a cyanide, you'll increase it quite dramatically. So much has been done in this area that you can actually create a broad categorization of all of the different ligands you could potentially put on a metal center. And you can characterize them by sort of what their impact is on the field splitting, and that essentially gives rise to what we call a spectrochemical series. And the characterization is really on the lines that we saw before, which is that things that are very, very weak field meaning that they give rise to a very small splitting, are things that, for example, are not only weak sigma donors, but they're also very, generally pretty strong pi donors, right? And that pi donation serves to actually lower the energy gap, and see things like iodide, bromide, chloride, sulfide, fluoride, etc. Right? Then you have things that are essentially not very good pi donors that are essentially only sigma donors, things like water and ammonia. And then you have things that are very good pi acceptors, and these pi acceptors are the ones that are going to give rise to very, very large splittings, whereas the sigma only case will be at some intermediate level, and these pi donors will, of course, create the small split. Now, this factor of the nature of the ligands is, of course, a key determinant, but it's not the only determinant, right? So the oxidation state of the metal ion, or the number of electrons in that metal ion in the d manifold, also matters an awful lot. And by the way, you'll all get these notes, so you don't need to take a lot of notes, but anything that helps you, feel free to. So the general trend is that for any given metal ion, as you increase the oxidation state, what you tend to do is contract the distance between the metal and the ligands. And as a result of that, you create more repulsion, and as a result of that, you also tend to increase the splitting. Right? So the general feeling is that if you have a higher oxidation state metal, the ligands come in more, and because that means there's more interaction with the metal orbitals, you'll tend to cause a greater splitting in the ligand field. And this you can kind of see broadly with some characteristic examples. So chromium, hexaachol in the 2+ versus 3+ oxidation state, you can see a pretty substantial change in the splitting. The same is the case for the vanadium between the 2+ and the 3+ oxidation state. The same is the case for cobalt, the 2+ and 3+ oxidation state. So in general, as you increase the oxidation state, the splitting parameter increases. Just bear with me for a few more slides, because the reason we're talking so much about this is that these ligand field parameters impact ultimately reactivity. The other thing that you can think about is, what if I have the same oxidation state and I simply move across the periodic table? Well, what will happen in particular? What happens if I move down in the periodic table? And the general trend you observe is that field strengths tend to be comparable between the second and third row, but those tend to be significantly higher than that of the first row. And so first row transition metal ions tend to have relatively weak ligand field strengths, whereas these other ones tend to have relatively high ligand field strengths. And this has mainly to do with the radial extension of the second and third row transition metal ions, meaning that there's better overlap with those ligand-centered orbitals, and as a result, that causes a greater degree of splitting. Here's one example where you can take a look at this. The same compound here, cobalt hexamine, versus that of rhodium and iridium. Remember, all of these three ions are in the same row of the periodic table, same column, I guess, of the periodic table. And you can see here a systematic increase in field strength, with perhaps the most pronounced effect really being here, and then to a slightly lesser extent. Okay, does this make sense so far? So these are some general trends, right? So when you're thinking about whether something will be strong, very, very large ligand field splitting, or a very small one, you want to consider, one, what's the nature of the ligand? Two, what's the nature of the oxidation state of the metal ion? And then also where it is in a given column, right? Whether it's in the first row, the second row, or the transition series. So why does all this matter, right? So in general, things that have relatively small ligand field splittings tend to be ones that also tend to exchange their ligands very, very rapidly. And part of the reason for that is if there's a very, very small ligand field splitting, there's a greater likelihood there will be electrons populating those antibonding orbitals, right? And as a result, what you tend to get, and there's a lot on here, so let me just kind of walk you through what you're looking at here. So consider what we looked at just on the last slide. Like iridium is a metal that's one on the third row of the transition series. In a high oxidation state like 3+, it is inert as inert can be, right? So what this is a plot of, let me just kind of orient you, right? So this is the lifetime. It's actually done entirely for water ligands, so that we're not even taking into account here differences in the ligand. It's just asking, if I have a water on an iridium-3 center, how long will it take for it to exchange for another water in solution? And the remarkable thing is you need to wait 10 to the 10th seconds to see that exchange on an iridium-3 center, right? That's an enormously long amount of time, right? It can change by quite an amount if you simply move one row up in the periodic table. And you can see some dramatic differences simply between different oxidation states, right? So consider the ruthenium-2 ion versus that of the ruthenium-3 ion, right? We said as you increase the oxidation state, the field strength usually increases, and you can actually see as a result of that, the metal-ligand bonding strengthens, and there's actually an attenuation in how fast the exchange is. Or in other words, I have to wait longer for the waters to exchange with something in solution. Right, and you can see this kind of all across the periodic table in general with your first row transition metal ions in their low valent oxidation state being the ones that exchange quite rapidly, right? So you can see that here, iron, cobalt, manganese, all very, very fast exchanging ions. What's even faster is something where you have a full D manifold. That means all the ligands have significant antibonding character. So things like zinc, cadmium, Even for iron, when you go from 2+ to 3+, there's a pretty dramatic difference. Here's one of the most pronounced differences. Consider that of chromium-2 versus chromium-3, right? That's a change by, about 16 orders of magnitude, which is pretty amazing. And so you can see there's a lot of variation you can get in the sort of time scales for ligand substitution by virtue of the electronic structure and the field strength of the metal center. And that'll be a big subject of what we actually look at. All right, does this picture make sense? And again, you can rationalize most of these trends by what we showed in the last few slides. All right. So the next thing we're going to go to is, this tells us a little bit about how fast something will exchange. Let's ask a little bit more of a subtle question. What are the mechanisms by which ligands can exchange? And we'll kind of walk through this. How many have had a kinetics class of some form or another? I know we teach a little bit of it in probably 511-2 or one of the subsequent classes, but nonetheless, we'll get everyone on the same page here. Okay. So let's take, for example, again, this molecule that we looked at before, cobalt hexaamine, 2+ ion. And let's ask the question, let's just postulate a mechanistic sequence for the ligand substituting with another ligand, right? So first thing I'm going to postulate, and this is just a mechanistic hypothesis, that the first step of a ligand substitution is that one of the amines pops off. It's a perfectly reasonable elementary reaction step that I've invoked. An amine dissociates from the compounds. And then upon dissociation of that amine, a new ligand then binds to the compound. Okay, fair enough. And so, if this is in fact the case, I can go one step further in this mechanistic sequence and make a declaration or make a hypothesis or a postulate about which of these two steps is going to limit the overall rate. Right? So remember, in a multi-step sequence, there's oftentimes one step that ends up being significantly slower than the other steps. We call this the rate-limiting step. And I'm going to, for the moment, simply postulate that this first step is rate-limiting. Okay. So in the limit that this is in fact rate limiting, we would then postulate that that subsequent step is actually fast. And so the question that I'm going to ask, and I want you to kind of work together on this for a few minutes, and maybe talk to your neighbor, is to write a rate expression for the rate of this overall reaction. Okay, so I want you to write a rate law for describing this substitution reaction. How are we doing there? How many, by a show of hands, feel they have something they're pretty confident in? Okay. And how many, by a show of hands, feel we should go over this in some detail? Okay, great. Let's go over this in some detail. So how do we construct a rate expression for a sequence, right? So the first thing we've got to look at is what is the rate limiting step? And the best place to really begin is to ask, what are the reaction partners in the rate limiting step? Because a thing that is a reaction in the rate limiting step will, at least in terms of deriving our rate expression, be where we begin. So if we say that this first step is rate limiting, what are the reactants in this rate limiting step? What's on the reactant side of this arrow? Just this compound, right? So just the cobalt hexaamine 2+ ion. And so we know that the rate at which this will occur will of course be dependent on the concentration of the species, right? The rate at which the reaction occurs. And it will be dependent on a rate constant, right? Just a concentration independent term, a constant, that will then characterize the rate. And I've actually put that value here as K1 here, and then a different one as K2. So those are the rate constants for each of these reactions. So then all that's necessary in this elementary sequence, that's essentially a unimolecular reaction, is simply to appreciate that the velocity of the reaction is simply going to be related to the product of the rate constant and the concentration of the species. If I have more of this, the velocity of the reaction will be greater, right? Because it's a reactant in this. Does that make sense? So, okay. So if in fact this is the case, right? Now, is this an overall rate expression? Well, in this case it is, right? Because we know how much of this we put in a solution. It's the starting material. And as a result, we get a velocity of the reaction that's simply related to that rate constant of concentration and mean. And so we can ask some questions with this rate expression. So the first question I would ask is, what if we made L, the new incoming ligand, a better nucleophile? Would that alter the rate? How many say yes by show of hands? How many say no by show of hands? Okay, great. So I presume the logic there, right, is that the interaction of this new ligand with this intermediate only exists past the rate limiting step. And in fact, the identity of L or its concentration are not in the rate expression. And as a result of both of those, irrespective of what we do to L as a nucleophile, provided that we have this same mechanistic sequence, we would expect no change. Those make sense? Okay, let's consider an alternative reaction pathway, right? A dissociative ligand substitution. So in this situation, let's take the exact same mechanistic sequence, but let's now designate a different thing happens. Rather than this amine dissociating in a rate limiting step, let's say that it instead dissociates in minor equilibrium, in an equilibrium process. That's to say that the amine pops off and then it comes back on. Pops off and it comes back on. It probably does that millions of times before ultimately the rate limiting process happens that captures that intermediate and takes it on to product, which is now the new incoming L to do the ligand substitution. So we've written exactly the same rate expression, right? But what we've done is invoked now that rather than this step limiting the rate, we're saying that this step limits the rate. And as a result of this step limiting the rate, this has the ability to go back and forth really unfettered or in unconditional equilibrium on the time scale of the overall reaction. Does the distinction there make sense? Right? And the first one we're saying the first step is what's gating the rate of the overall reaction, and the next one we're saying the second step gates the rate of the overall reaction. So now I'm going to ask again for you to take a moment and write a rate expression for this sequence. This is obviously a little bit more complicated, right? Because the logic is still that we begin with what are the reaction participants in the rate limiting step. And because that is an intermediate, we need to rewrite that in terms of starting material. So if you follow that logic, take a few minutes and write out a rate expression for this sequence, and then we'll discuss it. Everybody feel okay here? Why don't you discuss it with your neighbor and convince them of the rate expression? Does everyone feel they have something that they've agreed upon? Okay, does someone want to walk me through what would be the first step in writing this rate expression? Okay, go ahead.
Find the rate limiting step, which is step 2.
Okay, great. And what would be the rate law for the rate limiting step?
For the rate limiting step, it'd be K2 times intermediate times the incoming liquid file / ligand.
Great. So I think you said basically this, right?
Yeah.
That the reaction velocity is related to K2, the rate constant of the rate limiting step, the concentration, and of course also the identity of the incoming ligand. The identity would be appearing in altering the rate constant, and then the concentration would be appearing explicitly in the rate expression. And then we need a concentration term that's related to the intermediate. Okay. So now we can apply an approximation known as the steady state approximation, which is simply saying that in the limit that this reaction is occurring in a situation where this is rate limiting and this is in equilibrium, what you can actually assume is that the concentration of this intermediate remains essentially unchanged over the course of the reaction, where the variation in the concentration of this is not changing with time, and as a result, the rate of its production and consumption via all of the possible pathways in this sequence in aggregate will equal to 0. That's the only way that I can make sure that its concentration remains unchanged. And so in the limit that its concentration remains unchanged, remember that the rate of formation of this intermediate is related to K1 times the concentration of the starting material. The rate of disappearance of this intermediate is now related to actually 2 steps, right? One is going to be the rate limiting step. That's the same, what we wrote up here for the rate expression, K2 times L times the concentration of the intermediate. But it can also be removed via a different pathway, which is simply the backwards of the first reaction, right? And that backwards of the first reaction is K minus 1. Now, importantly, right, it's going to be multiplied by the concentration of amine. Unfortunately, I didn't write it here, right? But remember, the balanced reaction here is this going to this plus the ligand that dissociated, right? We can't lose that. We can't lose accounting of that, right? Because it left, it's a participant. In fact, I need that amine in order to make this go back to this. And as a result, that rate expression is K minus 1 times the amine concentration times the concentration of this amine. Does everyone follow how we wrote this? Okay. And the value of doing this, right, is that we now have an ability to solve for the concentration of the intermediate. And remember, the concentration of the intermediate is an unknown quantity, right, over the course of the sequence, because we oftentimes have no way of actually explicitly observing it, especially if it is in very minor equilibrium. And what we can really only change here is the concentration of the species that we put in. And so to write this rate expression in terms of those concentrations, we can rewrite this, and all we're doing is some simple algebra here. And what we get here is K1 times the concentration of the starting material over K minus 1 times the concentration of the amine plus K2 times the concentration of the right? And if we substitute this into this overall expression, we get this, what seems like a little bit more hairy or complicated rate expression, but it really isn't that complicated. What we now get is K1 times K2 times the concentration of L times now the starting material over K minus 1 times the concentration of amine plus K2 times the concentration of L. Okay. So we can also take a limiting case of this, right? And a situation where K2 times the concentration of L, because it's rate limiting, is very, very small relative to the back reaction, K1 times the concentration of the amine, allows us in principle to make a simplifying assumption that this term doesn't matter as much as this other term. And the limit that we say this term doesn't matter as much, so much so that we can ignore it, what we get instead is a situation where the K1 over K minus 1 is simply the big K1, the equilibrium constant for this reaction, times K2 times the rate limiting step times L times the concentration of the starting material over the amine concentration. Now the importance of this, right, is that this gives us really powerful intuition about how this system will behave. Right? It's telling us that if we, for example, increase amine concentration, what would we expect in terms of the rate?
Rate depression.
Yeah, so the reaction would have an inverse reaction order by virtue of it being in the denominator for this reaction. And that's reasonable, right? Because this, we're saying, is in essentially equilibrium. And because ammonia is a product of the equilibrium, when I add more ammonia, I shift this equilibrium more to the reactant side, and that inhibits the overall reaction. Right? And likewise, if we vary the concentration of L, we would expect an acceleration of the rate. And so kind of you get a lot of intuition about how exactly this situation goes. And so we kind of answered this, right? One of the ways in which we would distinguish this from the previous case is that this reaction would be dependent not only on the concentration, but also on the identity of L. And it would also depend in an inverse fashion on the concentration of the mean. And what's powerful now is you can use experimental information about how the rate varies as a function of the concentration of these species to be able to then infer what the mechanistic sequence is. Okay? This is kind of the heart of mechanistic inquiry, right? Something our group does all the time, and I really believe is a sort of a noble pursuit in chemistry. Right? Because what we're really able to do is use the mathematics and the kinetics of the system to learn something that we would be really almost unable to be able to know by any other method. Right? And that's a kind of an awe-inspiring thing to be able to do. Okay. Let's consider one other pathway here that is a little bit different because the geometry of the metal center is different. So let's consider a dissociative ligand substitution. Or sorry, this title's wrong.
Pizza?
I don't know, did we order pizza? I mean, we shouldn't have refused. Okay. So sorry, the two, the title of the slide is wrong, unfortunately. I apologize for that. The previous two cases were dissociative ligand substitutions, right? Insofar as a ligand came off and then a new ligand came on. You can also have what's called an associative ligand substitution. This tends to happen for square planar compounds, compounds that are not octahedral geometry but rather square planar. And in this sort of a sequence, what you can have is where the rate limiting step is the incoming new ligand, right? And so the new ligand binds, and then that induces dissociation in a fast step of the old ligand. Right? And now the rate expression for this would be very similar, really, to what we saw before, but a little bit more complex insofar as that we wouldn't have just a dissociative substitution where it was only dependent on the concentration of this. It would now be dependent also on the concentration of the incoming ligand. And so a rate expression for this is just K1 times L times the concentration of the compound. Note importantly that we don't have here, for example, an inverse dependence on the amine, right? Because dissociation of the amine occurs past the rate limiting step. And what this is really gated by is how the new ligand comes in and binds a starting agent. Okay. Does this make sense? Okay, now in this situation, if we make the L far more nucleophilic, right, we would expect a variation in the rate, right, because that's what's gating the rate. Now remember that for a dissociative ligand substitution, in a situation where the dissociation step is in quasi-equilibrium, you can still have a dependence on L. But the rate expression will be different, right, because the dissociating ligand, it will be inverse order. So you can tell these things apart if you know all the reaction orders, right? And in this situation, you would certainly see a strong rate enhancement for changing the nature of the L. Okay. So we just have two more slides here to kind of get a sense for a couple of other peculiarities of how you do this, right? Or some other ways you can learn something about mechanism, which is not only by inferring the nature of the reaction orders for the relevant species and then using that to infer a mechanism, but you can also determine something about the activation barriers for the reaction. So remember, when we had an expression that was, say, a dissociation that was rate limiting, we wrote a very, very simple rate expression, where we had the velocity of the reaction related to a K, a rate constant, and the concentration of the species. So if we have a way of measuring this rate constant, we can ask a simple question. How will this rate constant depend on the temperature? And this is the Arrhenius equation. What this is essentially telling us is that there's some prefactor that's temperature independent, and there's an activation energy for the reaction over RT that determines the ensemble rate constant. What this is essentially saying, of course, is that if you increase the temperature, you would expect the rate to increase, and there's an exponential relationship with that. And so you can actually make an Arrhenius plot by noting that in a logarithmic form, if you take the natural log of the rate constant, what you'll get out is a natural log of the prefactor A minus E activation over RT. right? And that means if I plot 1 over t versus the natural log of the rate constant, or rather the natural log of the rate constant versus 1 over t, what I should expect to get is a straight line, right? And this straight line will have an intercept, a y-intercept, that would be related to the prefactor term. And it will have a slope, importantly, that will simply be equal to the activation energy overall. Right? And what is powerful here, right, is that this gives us some information now about what is really gating this reaction, so we can be more quantitative in terms of what the rate constant is, and translate that into an actual energetic quantity that we can then even compare with a computation. And people do that quite regularly. Let me ask you this. So what would be the possible case in which an Arrhenius plot would be nonlinear? So I'm kind of showing this idealized situation where I vary temperature, and I haven't put any numbers on these axes, right? So I could be varying temperature by hundreds of degree Kelvin, or I could be varying it by 10, but let's just say I varied something over a fairly wide range, and I got a situation where it was not a linear plot, but really had sort of 2 slopes to it. What might that indicate?
Activation energy changes with temperature.
Yes, that's one possibility, that the reactivation energy has changed. There's another possibility also we want to go with.
Possibly a different magnitude.
Yeah, right. So you can have a situation where the activation energy makes, for example, K1 change in a way different than, say, K2. And as a result, when I walk between temperatures, I could get a situation where what used to be rate limiting in one temperature regime is no longer, and then I get a different rate expression. And then if you redid kind of the reaction order studies in that new temperature regime, you'd see a different rate expression. When you saw the exact same rate expression over all temperatures, then you know that you actually have a temperature-dependent activation energy, and that can also happen for other reasons, depending on the entropy term and other factors. Okay. So this is kind of what I wanted to tell you about kind of the bare bones of how we'll treat kinetics in this lab. The last thing I wanted to leave off with is, how do we actually measure the rate, right? And one real powerful way for measuring the substitution of ligand compounds is to use UV visible spectroscopy, and this is what you'll be using in the lab, I'm pretty sure. And the reason is that if you change the ligand, right, we know that we should expect a change in the color. And if we expect a change in the color, we ought to be able to monitor the change in the color to give us diagnostic information about whether the ligand actually has changed. Right? And so how do we actually do this? We measure a UV vis spectrum, and what really a UV vis spectrum is absorbance on the y-axis versus wavelength, and that gives us sort of a characteristic fingerprint of a molecule. And when we see a molecule change from one thing to another, we'll see those fingerprints change between each other. And by tracking how quickly they change between each other, we get information. So the question is, what really is absorbance, that y-axis, right? And absorbance is really determined by well, first for a moment, we can look at how the spectrometer actually works. So what you essentially have is a broadband light source, usually a deuterium lamp or a tungsten lamp. It gets focused on a mirror, and it goes through a filter. And this filter will essentially produce monochromated light. So it'll essentially split that broadband spectrum into little chunks. And the little chunks will be over a narrow window oftentimes a very narrow window in the wavelength, right? And because it'll monochromate the light, or take only one color of the light, it'll then send that to a beam splitter. Some will go through the sample, and some will go across a mirror against a reference sample. And because you have these two, what you're essentially going to do is have one with your sample in and one with none of your sample in, just solvent, for example. And because you have a photodiode that will essentially measure the flux of the photons, what you'll essentially get out is a flux of photons here versus a flux of photons here. Obviously, the flux of photons here will be higher because you have nothing absorbing the light. Here, something's absorbing the light, and so the flux of the photons is lower. And if you essentially ratio those intensities, the intensity coming at the photodiode in the beam path going through the sample versus the intensity of the photodiode coming through the reference sample, what you can do is take a ratio of those, and the ratio of those is the transmittance, and the negative log of that transmittance is the absorbance. Now, why do we go through this sort of kind of arithmetic gymnastics to be able to do this, right? Why don't we plot the transmittance? And the main reason is that absorbance, because of the way this is done as a negative log of the transmittance, is actually related via the Beer-Lambert law in a linear fashion to the concentration. So for any given absorbance, you have this epsilon, or an extinction coefficient, times the path length L of the cell. Here, these are actually given here, so I'm just going to show you, right? So epsilon is the molar absorptivity, or for a given concentration and a given path length, you have a certain absorptivity. If you then know the concentration, the path length, and the extinction coefficient, you can take any absorbance and back out a concentration, right? Simply by dividing by the molar absorptivity and the path length. And the path length of most cells is 1 centimeter, so it's pretty easy. You just take the absorbance and divide by the molar absorptivity. Now, there are some caveats to when the Beer-Lambert law is actually valid. It usually is only valid when you have dilute solutions. Homogeneous solutions, when something is heterogeneous, it's a little bit more complicated. And also you need something where you don't have a concentration-dependent reactions. So for example, if I had a molecule that was absorbing some light, and when I went to very high concentration, I caused the molecules to dimerize, obviously that may change the absorption characteristics, and it would no longer behave according to Beer's law. And what this means, of course, is that you can replot any UV vis in terms of extinction, right? And this is really powerful, right? Because you then know the spectrum of a molecule as a function of its extinction coefficient. That means that if you collect any other spectrum with this, by simply knowing this reference value, you can get out the concentration you're seeing. Right? Because you know the absorptivity at every single wavelength, and that's essentially what an extinction spectrum is. All right, so what you'll then be able to do, right, is use UV vis spectra collected over time to be able to know the concentration of species over time. And you know the concentration of reactants and products over time. By knowing that, you get the rate. Now, UV vis is only one way to measure rates, right? There are many ways to measure reaction rates. You can measure it by vibrational spectroscopy. You can measure it by really NMR as well. It's a nuclear magnetic resonance technique for monitoring reactions to products. You can also measure it electrochemically for electron transfer reactions, something our group does a lot of. And so all of these are really tools to be able to get at rate. And then from that, you can infer mechanism. And from that, you can really kind of put together a mechanistic sequence for the steps that go between reaction and product. So that's all I had for this right now. And you now know, hopefully, enough to be able to kind of get a broad overview of what happens in this function. And Marius will post the lecture?
Yes.
Great. So we'll be all set.